Yeah, thanks a lot. Yeah, so it's about a subtopic, right? It's about knowledge representation and reasoning for cognition-enabled robot manipulation. So yeah, so let me just recapitulate what I have talked about in the first lecture, right? So I think the key points that I wanted to get across, that if we are looking at cognition-enabled robot manipulation, the key task is that the robot gets underdetermined tasks, something like set the table, bring me something to drink, and the task of the control system is to compute a body motion of the robot, so basically voltages for each motor in the joint that achieves the desired effects and avoid the unwanted ones. So that's kind of the heart of when we do task-oriented manipulation, right? And there are kind of two other constraints which make it actually cognition-enabled. And one of these aspects is that the robot is understanding what it's doing, so that it can answer open questions about what it's doing, why it's doing, how it's doing it, what it predicts to happen when it's doing it, and that it can take advice, right? That it can take information from a human and actually translate it into action, right? So that's kind of the key thing. So I was basically looking at our approach at doing that, and the key idea is that we kind of frame the problem that we believe that there are generalized action plans that are stereotypical, that are patterns for doing that, and there are concrete motion plans which basically we can look at. So Alessandra was talking about how important it is that the robot moves like a human to have the implicit communication going, right? So we want to have our motion pattern plans actually being informed by cognitive psychology, human action science, so that we have a good mapping, right? And the key is how to get from these abstract plans to these concrete motions. And the approach we are choosing is that we are using knowledge and reasoning, and that we use it to contextualize an abstract plan into concrete motion, right? And the idea is we have the abstract plan, we have knowledge chunks, which are general and reusable, and this makes actually the robot scale to open world. And we had a kind of an example for how does that look, and we had seen that in the demo for the table setting, right? So the robot gets a vague action description like put a cup on the table. It takes that very vague instruction, instantiates the general action plan, right? And it extends the action plan with the parameters of the motion plan, and then it asks kind of the fundamental query, the body motion query, namely, what are the instantiations of the parameters of my motion plan that actually, that again, this brings in Alessandra's point about prediction, that achieves the desired effects and avoids the unwanted ones, right? And that's kind of the huge inference problem that a robot control system has to solve in a pervasive manner, kind of for all actions that it executes, right? And if we are taking that kind of perspective on robot action, the key workhorse in the whole thing is contextualization, right? So it's actually how do we actually get that going, right? And if you're looking at that, from that perspective, if you have your context-specific body motion, like picking up a heavy pot with two hands, and you have the vague task request that leads to it, the difference has to be in the knowledge and the reasoning of the robot, right? And that's kind of the only place where it can, if you are buying into that perspective, right? And what I do in the lecture, I talk about the knowledge and representation and reasoning that is necessary for doing such things. And we do that in the context of our architecture. I also had that in the last lecture. So we have talked about almost all the components, but the knowledge representation and reasoning system, and that's what the topic is today. So let's take a step back. So it's always good to kind of have a perspective on the problem. So the perspective on knowledge representation and reasoning is that these should be the cognitive capability that enable robot agents to act successfully in the physical world and also to know and understand what they are doing. And we are doing that through a specific combination of methods, right? We are doing that basically by reasoning and learning enabled by representations of models targeted at future hypothetical intended actions, right? And that means, if we are talking about actions, that means we are talking about tasks, we are talking about the body motion and the causal physical effect that these body motions cause in the world, right? And we have to get that going. And again, so if we are talking about models, it's the question of, if we look at the human and the robot, do they share the same model, right, about the tasks? And we want basically models in the robot control system, in the human, that match each other, right? And we want to represent these models, right? We want to represent these models because the representation enable us to ask specific questions about the models and obtain the information out of the control system, and we want to reason them. And turning things into representations is a kind of a very good vehicle to doing that, right? Because you have representational entities that you can link to your prior knowledge and that you can use in order to do that. So I want to go through these different aspects. I want to go through models and how they are represented, and I will start by looking at how people in the community have done that before. What are the kind of the traditional models, right? So the traditional model that everybody gets to know if they take the Russell Norvig book is that the conceptualization is that we have a robot agent, and the robot agent interacts with an environment through body motion and captured images, right? And kind of the environment is composed of objects. The body motion causes changes in the environment, and these changes can be seen by the camera system. And what we are really interested in is we want to have this cognitive function that solves the body motion problem, right? So we want to know, how should I actually actuate my motors in order to do the right thing? So that's kind of the big picture of what we want to have in the head of our robot. So traditionally, so these kind of models that we are looking at in artificial intelligence, they are very old, right? So they are from a time where people programmed with punch cards, where kind of we had very little computational power. So these models are extremely sparse, right? So they are very abstract, and this is kind of a typical model of how the actions of robots are represented, right? So we have entities in the world that are some things like pot and some popcorn kind of thing, and kind of the environment is structured in two objects that have parts, but again, the parts are abstracted in a very abstract way, right? So we have a right drawer and a left drawer and the left part of the tabletop and so on. Similar if you're looking at actions, right? Actions are kind of atomic things, right? So they kind of have names, they have parameters, so we might have an action fetch and place with the parameters object from to, and they have preconditions, so I can only pick up an object if my hands are empty, and if I do that kind of successfully, then the object will be at the destination at the end. So what that does is, so we basically have as our basic model of the world a state transition system with atomic state transitions, right? So we have states, and if an action precondition is satisfied by the state, an action can be performed in that state. If we look at the effect specification, that tells us what the successor state is. So basically that implies a graph on states of the world that are connected by actions, right? And that's kind of the way the robot can change the environments. And then the problem solving of the robot is then simply, we are looking at the current state, we look at the state where the goal condition, the goal that we have, is satisfied, and then we look whether there is a path from the current situation to the goal state, and this is the plan that we have to execute in order to achieve the goal, right? And that's kind of the basic model that robotics is essentially using for doing these things. So now we can have a look at how should we actually represent that model, right? And I think one of the most successful models of representation is a logic-based approach, right? So logic is a symbolic language, and it gives us the means of representing our model in a very compact way that aligns to natural language, right? And that allows us to make inferences about the model, right? And the reason logics are such cool tools for artificial intelligence is that they have certain components that work very, very well for our purposes, right? So they are actually the combination of a syntax, a semantics, and a calculus. The syntax tells us how can we encode our model, how can we represent it in terms of symbolic structures. The semantics tells us if we have some symbolic structures, what do they actually mean? Are they true or false? And the calculus says how can we actually transform symbolic structures into other symbolic structures, right? So if you're looking at it, so in our state of the world, so the typical predicate logic representation would be the cooking pot is on the right shelf, and we can have conjunctions of basic expressions, and we can have background knowledge like the cooking pot is a container, and thereby everything we know about containers is inherited by the cooking pot, and that helps us to reason about it. So the semantics is then that we actually take our symbolic names, we look at the correspondences in our model, and we draw a link from entities, from symbolic names to entities, and from predicates to relations in the world, right? And we're doing that. And the calculus is just kind of patterns of reasoning that just tell us if we have a symbolic expression, that matches this pattern, another one that we matches this one, then we can produce a new symbolic structure that is of this form, right? And the reason this apparatus is so cool is that we can design logics, right? We can design specific logics that have specific properties, right? And so in particular, we want to design logics where the semantics and the calculus are in a specific relation, right? And the calculus should be correct with respect to the semantics, right? Which means if we have true symbolic expressions, we apply the inference rule to these true expressions, then the resulting expression should be true, right? So everything that is computed by the calculus should also be true with respect to the semantics, right? And the second property is that the calculus should be complete. That means if something is true, then we should be able to kind of compute it with symbolic symbol manipulations that are prescribed by our calculus, right? And if we have these two properties, right? So kind of the big thing is that we can now formulate the problem of making correct inferences as a search problem, right? Because we simply can run and see what are the symbolic expressions that our calculus produces from our original knowledge, and we can then see if what we want to know is actually an instance of what is produced, right? And the big thing here is that now we have a very simple mechanism that can be automated in computer systems that don't understand anything in the world, right? But they are still only doing the right inferences, right? And that's kind of a very powerful idea, right? So the big thing is, so first we want to have have the logic in a way that kind of a formula is true if and only if it can be actually derived from the symbol manipulation mechanism, right? And then there is a second thing, right? So we want to have the knowledge bases such that they contain all the knowledge that we need in order to solve all problems in the problem domain, and which means the knowledge base should be strong enough that our robot can produce all the action it needs to perform all the tasks, right? And all the tasks are kind of achieved in the correct way. And that makes it extremely powerful, as you can imagine. And even if you can basically implement part of your robot control system in that framework, right? So you have explainability, you have correct inferences, and certainty in these kinds of things, right? So, but we have problems with the model that is underlying that, right? And some of the things that are very problematic is that these models are far too abstract, right? So they are talking about actions as atomic units, but they don't say how the actions should be executed, right? And if you're a robot and you have to move your body, the how is more important than kind of the action itself, right? There's another thing, right? So if we have these abstract things, they are not grounded in the perception action system of the robot, right? So if we have a symbolic name, the question, and I see an image, so what is that kind of symbol actually meaning in terms of the image that I'm seeing, right? And we have to bridge that gap. In general, right? So kind of our knowledge base would not be able to answer questions about the images, camera images of a robot. And again, as Alessandra already pushed, it's the prospective capabilities that are really kind of the key for intelligent agency, right? So the robot has to, if the task of the robot is to produce a motion that achieves the desired effects and avoids the unwanted ones, then it has to reason about the future before it's committing to actions, and that has to be supported. Okay, so let's see, kind of, again, I'm only taking an example and our approach to taking that, but how can we fix that? So the way we are approaching the problem is that we are keeping the symbolic reasoning system as it is, and it's kind of perfectly fine. But we are combining the symbolic representation with an artificial world. And that's essentially, you can imagine it as a game engine world that is represented, right? And that game engine world, that artificial world, that gives you a rendering function, right? So you can take what you know in your symbolic knowledge base and you can simply render it. And it gives you a simulation mechanism, right? Because game engines come with a simulation mechanism, right? So the thing we are doing is kind of now the belief state and the knowledge base of the robot is not just a symbolic knowledge base, but it's actually a pair consisting of a knowledge base and the artificial world that knowledge base refers to. And this artificial world, we want to realize as a digital twin, right? So if we are taking our robot control program, we should be able to run that robot control program in that artificial world. And so we want our robot control program to simulate its motions and to kind of run its perception. And the robot control system does the same thing in the real world. And what we want to have is that both are so close to each other, right, that this is actually working, right? So that means we also have to adapt the perception system, right? So the perception system now, kind of the main task of the perception system is to go around in the world and rebuild the world as it sees it in the artificial world. So whenever it sees kind of objects in the world, it asserts these objects where it sees them in the artificial world. And now the upper part is artificial. And now, because we are doing that, because we are actually building up the belief state in this artificial world, and this artificial world is connected to a knowledge base, we can apply all the knowledge that the robot has and also all the experience knowledge of the robot to the object that it sees, right? And just at that moment, we are actually getting all our prior knowledge applicable to the current scene. And that's kind of very important. Of course, so what we want to do is, actually the game that we are playing is, we want to basically have our robot control program. And the robot control program should think it's acting in the artificial world. And it's doing everything in the artificial world, has perfect knowledge about. But in fact, it's acting in the real world. But kind of the amount of knowledge and information we have about the artificial world is so valuable, right? So that it actually kind of making this hypothesis pays off for this robot control program. We have to pay for making that assumption because kind of course, both don't fit to each other, right? So we have to have a heavy load of event detection, failure recovery in order to constantly adapt our artificial world to the real world, right? But the argument is that the inferential power that you get in your robot control system is so high, that the gain is so high that this pays off. So let's look at that pair, knowledge base and artificial world kind of a little bit more detailed. So if you think about it, so the technological developments in the last years, right? So one of the biggest technical breakthroughs are in virtual reality environments, in the way how we represent the physical world. So there are things now, we are looking towards metaverse, so everything that is in our physical world is at some point expected to have a digital replicate, right? So for representing this artificial world, we are using the scene graph data structures of virtual reality engines, right? And we see, when we see these virtual environments and how they work, that they have sufficient information in them, and they have them as digital representations in order to do that, right? And if we are looking at the scene graphs, we have our model inside the scene graph, right? So we have the robot agent, we have the environment represented, and we can use the infrastructure to infer the image that the robot is seeing, to kind of simulate the effects of the motion that the robot is executing. And we can also record everything in order to get imagined actions or remembering already executed action. So that's very cool. So just see if you're comparing the inferential power of these kind of these artificial worlds, right? So you get reasoning mechanisms that you don't have in symbolic reasoning. And one of them is mental simulation. So, so if we have that, right, we can take the current belief state of the robot and we can simply run another program, a hypothesis of what the robot intends to do, and it can look at whether that alternative makes sense by actually running a simulation, right? And see what will happen when the simulation is, when the action will be executed. So it makes sense just kind of to do that. And yet you see that when we are looking at these kind of simulations, they are very close to what's happening on the real robot, right? So we can also do mental imagery. So we can imagine what the cameras will see in certain points, right? And yeah, so here, right, when the robot looks at table, it can use its current belief state to actually populate how the scene should look, and now perception is not the question of what is out there in the world, but it is the question of do my beliefs still match the real world, right? Which is computationally a problem which is much, much better behaved than asking what is out there, right? And this helps the robot, and this is important, right? Because, again, if you think also about social interaction of human and robots, the robots have to be aware of the situation, of the environment, and that's just huge. That these are not just 10 or 20 facts you have in the knowledge base, but it's kind of the complete environment, right? Also, mental emulation. Again, Alessandra has talked about that, right? So that when you're seeing an action, you are actually replicating your action with your own mirror system and whatever, right? So if our robot is executing the action, it runs a mirror system, right? And the mirror system is the simulator in the game engine. So here you see the belief state of the robot, and here you see the real world. And what the belief state gives you, right, is that certain things you cannot perceive with your perception system, like that the object is falling out of the hand and where it might be, right? You get by running the simulation in your belief state, right? And so it's very powerful to run the emulation of whatever you're doing in your belief state in order to catch up with how the world develops. And so let's go to the second component. Again, so we have as our main implementation basis for our knowledge representation and reasoning system the scene graph data structure of the virtual reality environment, right? And what we want to have is we want to have a symbolic description and a set of facts about the world that covers every aspect of the world, right? And this is kind of very easy to realize, in particular if you have logic representations like Prolog, right? Because you can define predicates as a world through procedural attachments. Yeah? You don't have to state that fact explicitly as a symbolic structure, but it's sufficient to say, if you need to know that, this is the way how to compute it, right? And then the system only has to kind of infer dynamically what it needs to know, and that's the game that we are playing. And if we now take these pieces together and we see how is actually that fundamental question that we have, how do we get from underdetermined task requests to body motions, we can do it with our knowledge representation and reasoning system. So for getting the milk box out of the glass, we have here the symbolic queries that the robot has to ask, namely, well, the milk box is inside the fridge and it's standing on top of the shelves. That's at least what I have in my belief state. The fridge has a handle, and this is the articulation model of the handle. So when the robot is actually needing the information, it's able to extract that information out of the scene graph representation, and it looks to the robot control system as if it was just kind of a huge Prolog knowledge base, right? Which is a kind of a very convenient semantic representation that is very close to natural language. So these things are not only cool because of that, because we can ask our question, they are also, I think, they will be a fundamental step in grounding symbolic representation. So let me just kind of give some examples of what we can do with these kinds of knowledge bases. So we might want to implement a predicate expected image, right? So that's the image that the robot expects to see given what it believes about the world in the current state. So we are computing this predicate, right, by generating the scene according to our belief state, kind of putting an artificial camera exactly where we believe the camera of our robot is, and then we use a game engine in order to get the predicted image, right? Another cool feature of that is if we have the scene graph representation, we can make changes to the scene graph, right? So for example, we can tell the rendering engine each object part has a different color. And we can generate an image based on that. So this is extremely cool because now we can have another predicate depicted object, which basically takes an object, which is a symbolic name, takes an image, and we just have the pixel coordinates, and by just looking at the color, we get the identity of the symbolic name, right? So there is kind of a direct link. So if our control system says the image that I'm seeing and the image that I produce from my belief state, they are sufficiently close to each other, and then I simply take what my artificial world tells me as ground truth, try the action. If the action signals success, I simply assume that was right? And that's kind of extremely powerful. And another thing that you can also do is in your game engine infrastructure, you can assert that any other object but the milk box, they are invisible, right? And by doing that, you're getting a perfectly segmented picture of that you can, for instance, use for deep learning and other things. So, okay, another thing. So now we basically have a representation of the world which is very detailed, very powerful, that has kind of physics incorporated, and where everything has a symbolic, semantic meaning, right? Now, because we have the simulators in that game engine, and we can basically look, so this is work by André, we can look in the simulation engine what are the force dynamic events. Force dynamic events are things like the hand or the fingers having contact with the object being supported by a supporting surface or not supporting by a surface. But the point of these force dynamic events is that they segment the physics simulation, right? And into phases that are meaningful in action models used in cognitive science, cognitive psychology, right? So we are getting these force dynamic events, and now the manipulation actions, they are a grammar over these force dynamic events, which means we can pass the actions on the fly into our symbolic models. We are trying to push these actions as close as possible to physical reality, and but the big thing is really when you're acting in such a artificial virtual world, this artificial world is at the same time a prologue knowledge base. Every entity that you click on, you can ask about what are you, what can I do with you, and what has the robot done with you, and this gives actually a structural connection within your whole robot control system, right? And you can ask all these questions we had before. And you're recording, you're using that for imitation learning. You're recording the activities. You're automatically passing them into your action models. And now you can use them as a source of information to learn about the action. So here, it's an example where we are looking at scenes where the drawer was closed with a foot, and we are looking at the gaze and where the gaze actually looks when these things happen, right? So, and it's really, you can retrieve any piece of information you can express in your logical language, and you get it out of your experience data. So if you think about episodic memories and what would be a brute force way of implementing an episodic memory, the most naive way is just collect all the data that you're getting that way and see what you can make out of it, right? Okay, and that's what we are doing here. So we are running these interpreters. They produce semantic representations of that. We call them NEMs, narrative-enabled episodic memories. Oh, dang. I guess what's wrong. And yeah, and these you can access them through our open knowledge web service, OpenEase, right? So, and you can use them for your own research. And now, it's essentially that you have that powerful logical language that allows you to retrieve information from that, and you can do things like, I'm looking at an episode where the robot has picked up a cup successfully. I look at the begin and end of that sub-episode, and I want to draw the trajectory of the hand motion in that episode, right? And here you get all the links into your sub-symbolic recordings. So if we have that kind of infrastructure, if we can ask in that way, so then we can use that as drivers for huge machine learning problems, right? So we can take the question that we have. So we are looking for an action of the type pickup, where the object acted on is an object of the type pot, and the pot has a weight which is more than 2 kilograms, right? And we get these episodes. Now we are looking at the time instance where this task starts. And we are interested in what is the pose of the robot at that particular instance in time. Now we are using that inside a query that generates training data for a learning problem, right? So now we are interested in the set of all poses where we try to pick up a heavy pot and the task outcome was success, right? And we collect them simply in variable poses. And we do the same thing for the situations that where the action failed, right? And then we have the positive examples, the negative examples. We can make a supervised learning problem for learning the place where a robot has to stand in, or kind of suppose, in order to pick up an object successfully, right? And that's kind of what is done here. So here we have all our examples. The green ones are the successful ones. The red ones are the failed ones. Right? And now, depending on where the object is on the table, you learn the places from which the object can be picked up successfully. At execution time, you're detecting the object, but you have some uncertainty, right? So you back project the place according to your sampled position, and you get something like a distribution that is a measure of how confident you can be that your pickup action will succeed, right? And if you have here the object, the position, and the uncertainty of the object, you have here the place from which it can be picked up. And now we are varying the object position and the uncertainty, and you see that the whole thing makes sense, right? And now you can take that learn concept, right? And you can embed it in your perception action loop of your robot control system. So it has a symbolic concept, right? The place from which I intend to pick up the object, right? But in any iteration of your perception action loop, it updates what that place is, and according to the prediction of whether the action will actually be successful, right? And so the robot comes in, kind of the estimate became better, so the place becomes better. Suddenly it detects that it's not one object, but there are two, and now you see that it's kind of spread it, probability is lower, you get kind of another place on the other side, goes around, detects an obstacle, sees that it cannot pick them up in one go. One has to be picked up from here and the other one from the other one, right? But again, I think this gives an gives us some idea how future knowledge systems in robot control systems can work, where you actually combine symbolic knowledge representation and reasoning with the sub-symbolic mechanisms and how the two worlds can actually fit together. Okay, so 5 minutes you said, right? Yeah. It was your fault. Okay, so one of the things is, so we know that these virtual reality environments are cool, right? But we cannot have people actually kind of designing these environments and make them centimeter accurate and having that for all environments, right? So here's an example also from the startup Ubica, from a project that we had, where here's the belief state of the robot, here's the world, and now it's constructing a semantic digital twin automatically, right? So it has detected some base systems for the shelf. Now it's looking for the individual shelves. It has found them, add them to its belief state. It goes along individual shelves in order to find the barcodes and the separators. And now it uses that prior knowledge in order to see whether the product that is supposed to be there is really there, right? And by doing that, it can create these kinds of knowledge bases that I've talked about automatically, right? And it's linked to our knowledge system, OpenEase. So here you again have your query language where you can get information out. Yeah, and you get all the other functionalities. So that's. I just want to, just as a final thing, so as probably many of you know, we are just building up that new lab, right? And so I just want to talk a little bit kind of in the final how these things actually kind of relate to our new lab, right? So if we want to do cool research in cognition-enabled robotics, right? So we need robots, and the control system for that has to be there and accessible and maintainable. We need an environment and we need the human, right? So these are the three essential components. So these, if we want to do research with that, so these three components have to be available and accessible in three ways, right? So one is we have to have the real lab. We have to go in there with the robot and they should act. Then we need a very precise model of the lab, and then we basically need the digital twin and the simulation environments, right? Then we have the complete data recording and data interpretation infrastructure to make them accessible to the researchers. And yeah, and then I just run the video while I'm answering questions. So that's actually the digital twin of the lab, and I'm answering questions in parallel. So most of the things you have seen, right?
So thank you very much. That's already the first question. So it is working like this.
You can throw it. Yeah, so thank you. That was really very insightful. Is this working? Oh, yeah. It's great. Yeah, I just don't. Yeah, it's good.
Maybe it's not better.
Okay. So thanks a lot. I was wondering how would learning actually work when you perform an action in the simulation that is not yet known to the system, be it an action or a movement or the task? How would that work?
So if the human performs an action that the robot doesn't know of, or
yes,
yeah.
and maybe tells him, so this is now, I don't know, pouring water, but you don't know what pouring water is.
Well, I think for that you have to have the human, and the human has to teach concepts and things like that, right? So it would be actually the co-construction of understanding and the basic skills, right? And some of the things, kind of the robot would simply detect as surprising things, right? So it knows, for instance, when it sets a table and it sees the human performing the table setting in the virtual reality, it sees that the human was able to close the drawer with two hands being occupied by carrying something, right? Because it used the foot, right? So in this case, the game that we are playing, and Maren will also look into that, is that in episodic memories, we want to look to other ways where intermediate goals have been achieved, right? In ways that the robot would not have come up with, right? And then that would also trigger a dialogue between the robot and the human, right, to actually understand what is the rationale behind it, what is the causality that I need to do that, and that would be kind of a bootstrapping and also, it's kind of the way like humans would learn, right?
So is it currently already possible to insert like new knowledge into the knowledge graph, so to speak? So maybe
I think in the knowledge graphs, I think it's okay, right? I think it's much more complicated to insert that respective knowledge into the plans, right?
Yeah.
Because there it's not only kind of the knowledge, but it has to work in the context of the activity. But that is Arthur's thesis, right?
Okay,
thesis
thanks.
research, yeah.
I'll ask him.
Any further questions?
I can't.
Please don't hit the camera.
Thank you very much. I have a curiosity. So far, the representation that you're creating are as realistic as possible. So they are really capturing the reality. Are you envisioning the possibility to try and model what a human would see? Since our perception of the world is often wrong, I would say, or not accurate, but rather maybe we are focusing, we are hungry, we just see food, or in case of particular disabilities, you might not see the word properly. So I was wondering whether you foresee the use of that.
So there are also doctoral theses involved in that. So one is Farrosh. So he's looking into tracking humans, right? But then actually tracking the human in the form of an avatar, meta-human, I don't know. So it's an avatar that actually works in the virtual reality environment, right? And then there are things like a theory of mind aspects, where you basically put the camera where you see the eyes of the human that you see, right? And then you just take the rendered image of that and basically then look with the eyes of the human or with what the human, and Mona is working on that as well, on these aspects, yeah. Mona, not here. Here in the back. Yeah.
Thank you.
Yeah.
Okay. May we have to go to the break? So if you like to proceed to Michael, so ask him the questions. So okay, you are welcome to have another cup of coffee.
Thank you.
Thank you very much.